So just as a forewarning, this is a rather impressionistic talk. So please jump in with questions. Let me just give you the broad message, because it's easy enough to state now, and the goal of the talk is to give it some depth. So there's been, over the last couple of decades, a very rich dialogue between, I don't know, the community that does things like DG manifolds, higher structures, maybe Poisson geometry in the large, in a broad sense. There's been this rich dialogue between this community and the community that thinks about topological field theories. And there have been a lot of successes, so sort of central examples of this successful dialogue are, there are theories like Chern-Simons theory on the physics side. And this is connected with things like quantum groups and many other structures on this side. Another important example is the Poisson sigma model. Of course, classes of theories. It's related to questions like information quantization. Okay, so we know this stuff is good for topological field theory. And the main message is that there are rich opportunities for people here in a cousin of topological field theory, which I'm going to call holomorphic field theories. So I'm not going to define holomorphic field theory, but I'm going to give you an example that should give you the flavor of what I mean by this and also why I expect there to be opportunities. Okay. So I'm going to do a topological case on this side. So topological field theory, in this case, Chern-Simons theory. And I'll do the holomorphic cousin on the other side. So I'm just going to give a gloss of these. So the data to talk about Chern-Simons theory, you need an oriented, smooth, 3-manifold. Sort of our favorite one might be R3 with the orientation given by the usual volume form. Okay. You need to pick a compact Lie group. A good example to think of might be something like SUN. And you need a G invariant, non-degenerate, symmetric pairing on the Lie algebra of G. So think about the killing form, say. So this is the data you use to specify Chern-Simons. And then as a field theory, the fields would be the G connections on some principal G bundle over M. So this is some principal G bundle. And I think it's useful to just imagine you've fixed a particular connection so that you can identify this with one forms of M with values in the adjoint bundle of P. Okay. So for instance, if you had a connection here and I call my fixed connection D, I might think about there being a dictionary. Sort of locally, it looks like D plus A, of course. Okay. And then there's like what Kasia called equations of motion. These are the Euler-Lagrange equations for the field theory. And that says for Chern-Simons that the curvature equals 0. It's a zero curvature equation. That's, I mean, a very nice thing for a topologist. So in these terms, it looks like explicitly like that. That's the more Cartan equation that Ezra talked about a lot on Monday. Okay. And let me give a kind of moduli theoretic description of what I think Chern-Simons is about. So it's a zero curvature equation. So the moduli of solutions, I think the correct thing to think about if you're sort of a person from this community would be the stack of flat G connections on M. So if we fixed a principal bundle, let's just think about you take the connections that satisfy the equation modulo as a stack the gauge group. Okay. So let me describe the holomorphic side. So what we're going to do is promote things that are sort of traditional differential geometry to complex differential geometry. So M now is going to be a complex threefold. And I'm going to replace the notion of orientation with having a holomorphic volume form. So think about C3 with this volume form, for example. So this is sort of a weak version of a Calabi-Yau manifold. G is going to be complex as well. So we'll let this be the complex reductive group. Think about something like SLNC. And then we need a complex linear pairing. Same kind of data. Okay, so on the complexified, on the complex Lie algebra. So this is the data. Now the fields, I'm not going to take all connections. I'm going to take the del bar connections because I'm doing complex geometry. So I'll write this. To remind you of that, I'll write and this is isomorphic once you pick a point to omega 0, 1 of M with values in this complex vector bundle, the adjoint bundle. And the equation of motion is the del bar version of the curvature. So sorry, let me do that again. So we have this thing. And A is living in here. I want this to vanish. And that corresponds to del bar A plus 1/2 A equals 0. So that tells me that del bar plus A determines a holomorphic, the deformation of the complex vector bundle to another, holomorphic vector bundle to another holomorphic vector bundle. So let me just put it here. So solutions to the holomorphic Chern-Simons really have to be this holomorphic version of G bundles on M as a stack. Okay. So
is the action function similar to the Chern-Simons one?
Yeah, it's totally similar. So I was going to write that down next. I was going to write down this in the style of a, see if I can do what Kasha did. That was very fancy. Let's see. Oh, no, wrong way. Okay. Yeah, holomorphic principal bundle on the right-hand side. Just everything becomes the thing you would expect from complex geometry. Okay, so let me sketch a sort of BV description of both sides, which, yeah, so let me just say it and you can ask questions. So doing this BV thing is some approach to doing a DG manifold description. So the fields, I'm going to write it like this. They're going to be 1 forms on M with values in G. Let's think about, most of the time these bundles are trivial if G is, say, semi-simple. So this is the sort of obvious set of fields. And then we need to incorporate the fact that we really want to study things up to gauge transformations. So people in BV do the infinitesimal version of that. So this has to do with how this is a linearization. This is the Lie algebra of the gauge group and how it acts on the connections infinitesimally. Now, in the BV world, you also throw in a sort of version of the shifted cotangent bundle to this information. So we can think about 2 forms with values in G and 3 forms with values in G. And because we're on an oriented 3 manifold and we have this pairing on G, I can take something in here, wedge it with something in here, and use the pairing on G to get a 3 form, and then integrate. So you think about these as dual in some sense, and these as dual in some sense. And if you look at this, up to this funny grading shift, this just looks like the Durham forms on M with values in G. So it.
What is compactly supported to make sense of this pairing?
Sure, like we could take M compact to make it a good pairing. Otherwise, it's a pairing up into the density line, up into the top forms. It's like a local presentation of a pairing, but I agree you can't integrate it if M is open. So this thing gives you a shifted DG Lie algebra. If you shift everything up by 1, you really get Durham forms with values in G. And you can take the more Cartan locus, if you want, in Ezra's sense from Monday, to get some sort of, at least, very least, sort of perturbative approximation to this global moduli space.
Are you fixing connection to the order?
If you, in this case, yeah, okay. So here, let's take P over M trivial, and the base point is just the Durham differential. Okay. The action functional here, let me call it Chern-Simons, of a field A in here looks like this. It's 1/2 A dA plus 1/3 factorial. So you can see exactly where I'm using the data. Okay, so the holomorphic thing is very similar. In degree 0, I put 0, 1 forms on M, and I'm just going to put G here. If you had an interesting bundle, you'd need to do adjoint bundle. I'll just be lazy. And then we put in the dual fields, so 0, 2. Okay. And you again have a DG Lie algebra. If you shift up by 1, and let me write the action functional for holomorphic Chern-Simons. The only difference is that I'm going to use these same formulas, but when I do that, I always have 0 in the left slot. So to fix that, I need to put mu here. Okay. So hopefully this gives you some sense of how you might phrase these things in some of the languages we've seen this week. And hopefully also the dictionary is somewhat clear. At some level, we're sort of taking a Durand complex here, and we're writing down a Dolbeau version here. The Durand differential becomes the del bar operator. Everything else is pretty parallel. Question, yeah?
Sorry, what's mu?
Mu is this holomorphic volume form.
Oh, sorry.
Yeah. So this thing is a 3-0 form. This thing is a 0-3 form. So when you wedge them, you get a 3-3 form, and you can integrate. Okay, great. So it's fun to try to extend this dictionary. Anything you know about Chern-Simons, you could ask about holomorphic Chern-Simons. Okay, great. Okay, great. So now a question. Aha. Okay. Whew. A question to ask is, how do I find interesting holomorphic field theories to study? What are fruitful ones to study? Just like Chern-Simons has been so fruitful as a TFT. So there's a little bit of an art to this, but physicists have, over the last couple decades, they've gifted us with a number of remarkable conjectures and ideas using the following process. So there's a process by which they find interesting TFTs. So the process goes like this. Physicists have a collection of theories they already care a lot about, so supersymmetric theory. And I'm going to abbreviate supersymmetric because I'm going to get tired of writing it SUSY, SUSY. And they want a TFT, and there's a process they call topological twisting. This is due to Witten. So I'll tell you a little bit about what twisting means in a minute, but let me give you some examples just to orient you a little bit. So when the dimension of the field theory is two-dimensional, there's a class of script n equals 2, 2. That's sort of saying what kind of supersymmetry it has, so don't worry too much about it. Sigma model. And there's at least two kinds of twistings. You get the A and B models. And one of the remarkable things the physicists predicted was this process of mirror symmetry, that there were some dualities, that some of these theories behave exactly the same even if a priori they look different. Of course, that's a big business nowadays in math. There's lots of other examples, but let me mention a 4D example that has a lot of contemporary interest. So there's super Yang-Mills theories. These are gauge theories. And Kapustin and Witten gave us actually a whole bunch of topological twists. So they told us about these twists that give topological gauge theories. So these are some interesting 4D gauge theories. Probably the thing that's most exciting about them for a lot of people is that there's a conjecture that on the collection of supersymmetric n equals 4 Yang-Mills theories, there's this involution called S-duality. And two things that are identified in this involution are sort of equivalent quantum field theories. So Kapustin and Witten predicted that this survives the twist. So there's a version of S-duality over here. And they suggest that this yields or produces the geometric Langlands correspondence. After you compactify from a 4D theory to a 2D theory. So if you're on a 4-manifold, like a product of 2 manifolds, you kind of squish out one direction and just think of it as depending on the other. Okay, so that's a remarkable suggestion, and some people are taking it seriously and pursuing it in a lot of depth. If you have questions, Phil Song can answer them. Okay. So you might ask, okay, can I do some version that works that gives me a holomorphic field theory? And the answer is yes. So let me just gloss twisting what this process is, because I think it's useful to know about. So even if the rest of the talk isn't your cup of tea, I think it's a fun trick. So here's a gloss of twisting. So what does it mean to be supersymmetric? There's a lot of things you could say, but if you have a SUSY theory, what this means, among other things, is it lives, well, say on Rn, if you pick the Euclidean metric, or if you do a Lorentzian metric, maybe on Rn minus 1 comma 1. So, and it is equivariant, first off, for isometries of this space. I should be a little bit more careful about that. So the thing people really are interested in are the double cover. So something like spin n, if I do this right. So this is like translations is one of the isometries. The other is the sort of version of rotations, the spin cover of rotations.
Is it about like the superspace?
I don't want to talk about that. Yeah, sometimes you can do it that way. Yeah. But even better, but also for a super extension, meaning a supergroup of these isometries. Okay, so there's some extra odd part that acts. Okay, so this, as a remark, so this notation n characterizes the odd part of the extension. There's some rules about what kind of supergroups you allow. Okay? But regardless, there's a Lie algebra. I'll just call it SUSY n. I'll only call it little n to tell you the spacetime, and big N. And it's going to be acting on the theory. So it's really a question of representation theory. There's some super Lie algebra, say, acting on this theory, or the contents of this theory. And so now a twist is an element of the it's the odd component that self brackets to 0. Okay, I want to remark that one neat thing about this is that now if you view SUSY with this differential, this is a DG super Lie algebra. It's a Z2 graded if you want, it's Lie algebra with a differential. Okay. So that's what a twist is. That's just an element of the Lie algebra. And I've just told you I can kind of deform the Lie algebra to a DG Lie algebra. I can also deform the theory using Q in practice. So in practice, what this means, in the BV approach to field theory, the theory, the observables on the theory, has a differential which is supposed to be this anti-bracket with the action functional. The twisted theory just has the differential. You bracket with S, but then you also act by Q. So when you do that, it's maybe not a surprise that this DG Lie algebra is now a symmetry of this deformed theory. So going back to this picture, one way of thinking about it is that if you have a supersymmetry, it gives you a class of deformations of the kind of DG manifold of fields.
So this question, should I think of this SUSY and acting on the theory as a global symmetry, not as a local symmetry?
Yeah, it's global, totally global. This is like a finite dimensional.
So it's not already in the DD formalism.
Right.
So you have
Yeah. It's a global symmetry, right? It's like isometry. It's some fancy version of isometries. Okay? And the fact that it's odd also does something interesting. It's mixing bosonic and fermionic fields. But there's lots of ways they can get mixed if the odd part gets really big. Okay. And so, okay. Great. So let me just remark, maybe out loud. I should go up a little bit more, maybe. That in the theory, the observables are often complex valued. So actually, we can think about the complexified SUSY Lie algebra acting on it. And if you bracket an odd element with an odd element, you get an even element. And it happens to be the case that bracketing with Q always lands in the translation part. So if I've complexified the translation part, I have a C to the n. And so sometimes what you get is actually, it determines a complex structure. So these twists can determine things like complex structures on the space-time. I'll just say that for the specific case of 4 dimensions right now, so let's take the case n equals 2. I can think about bracketing with Q gives me a map from the odd component, and I'm doing everything in the complexified setting, to the even component in the complexified setting, but I'm saying the image has to do with R4 tensor C over R. We say a twist is holomorphic if the image is isomorphic to C2, because then it determines a complex structure on R4. If the image is everything, then in fact, the twist will give you a topological field theory. If it's sort of half of the translations, it gives you a holomorphic field theory. Okay, so if you take a supersymmetric theory on R4, you can use this holomorphic twist to get a holomorphic field theory. So we could try sticking in some of these examples here, for instance. Yeah, when it acts on the theory, you could think about it acting on the observables, and ours are complex valued functions, so that action actually extends to a action of the complexified Lie algebra. Yeah. It's maybe a little in the weeds, but okay. So the question I want to ask is, what if we play, Witten has multiple times played this game of taking things he knows about supersymmetric theories and turning them into statements about topological theories. Can we play his game here? What if we play Witten's game here? Okay. So let me write down an example. Just tell you the answer. I'm not going to show it to you. There's a thing called n equals 1 super Yang-Mills with group G. Think about something like SUN. Okay. Its holomorphic twist becomes something very nice. It becomes the holomorphic BF theory. And here I'm working, since I'm doing super things, this is all on R4. This becomes holomorphic BF theory with the complexified group on C2. Okay? So, let me write this theory on the right in BV style. So in degree 0, we have 0, 1, tensor G, the complexified G, I guess. 0, 2, we have 0, 0, tensor the complexified. Now we're in 2 dimensions, so this part truncates, but then here we have omega 2, 0, tensor GC dual, a complex linear dual, 2, 1, tensor the complex linear dual, complex linear dual. Okay, so this is usually called an A field. Something in here, it's called a B field. Not on the board very well. And for those of you who like BV stuff, this is the action functional. We can use the evaluation pairing between B del bar A plus AA. Okay. The equations of motion are quite nice. So they say that del bar of A, the one that has to do with variations in A leads, or B, I guess, leads to del bar of A is a holomorphic, is a del bar connection. So we're getting a principal G bundle. And the second thing is that B is holomorphic for this connection. It's a holomorphic for this connection. So a solution to the equation is a principal bundle and a holomorphic section of this funny coadjoint bundle. So the moduli of solutions, the moduli space of solutions is something like holomorphic maps from C2 in this case, T star 1 of BG. So you're studying a principal bundle. I could even put any surface in here, actually, any complex surface. It's a principal bundle. That's the map to BG, plus some extra data. That's this section. It's a section of the coadjoint bundle. Okay. But now I want to play this game. That was just a statement about the kind of example. The reason I brought up this example is BF theory is an example that people have studied a lot in this sort of broader DG manifold community. It's in 2 dimensions. It's a simpler sort of cousin of the Poisson sigma model. So you can borrow a lot of intuitions if you've studied those examples. And it's like Chern-Simons, but easier in most ways. And this is just a holomorphic version. But now let me bring in a much more interesting example, partly because it has a duality associated with it. So there's a prediction you might do if you're trying to play Witten's game. There's something people call superchromodynamics. So this means you have both a gauge theory and you have quarks and antiquarks. So you just take the usual setting for chromodynamics and you just turn it into a super theory. There's a way of trying to extend it. So this is the super Yang-Mills, and we'll do it with group SUN. But then there's some extra fields. There's a bunch of things called quarks. And I'll say that a physicist would say there's F flavors of quarks. And what that really means is that the quarks are some section of an associated bundle to SUN. So I need to give you a representation of SUN. So what I do is I take the defined representation and I take F copies of it, which you might think of as HOM from CF to CN. So this is some funny word physicists use just to tell you how many copies of the quarks you have. You have F different types of quarks, and you have F flavors of antiquarks. So this lives in the dual thing, so I'll write it as HOM CN to CF. That's the SUN bundle that we use to construct, SUN representation we use to construct the associated bundle. And sometimes people add other types of matter. We can think about quarks and antiquarks as matter of some kind. Okay. Let me just tell you what the twist is, the holomorphic twist. It looks like, I'm just going to tell you in terms of this moduli description, it looks like you're studying holomorphic maps, say from C2, into the shifted tangent bundle of, this is Stacky quotient, where V is a rep, and this should be the complexified, a rep of GC. So in our case here, V is this HOM from Cn to Cf, direct sum HOM from Cf to Cn. So this has very much, I'm trying to emphasize these moduli descriptions so that the connection with AK as Z theory is very clear. Okay?
That's your solutions.
That's the moduli of solutions, yeah. This is the solutions. This should be to the equations of motion. So this is maybe this is also, I should say, something of a conjecture in this talk, that if you really properly set up the theory of holomorphic field theory and of infinite dimensional derived differential geometry, then this is the sort of mapping space you would get for the space of solutions. Okay. Great. So now let me tell you if V were just the zero vector space, you'd get back BG. Okay? That's what we were doing up here. So if there's no matter, we'd be getting back BG. Now, this kind of thing, studying maps into this kind of stack, well, this is the kind of stack that's central to a lot of geometry. So it's a very natural object to study if you're a complex geometer, even if you don't care about field theory. But now let me tell you an interesting claim about what happens in superchromodynamics. So I need more space for this. Let's see. Okay. Okay, so Seiberg conjectured something about this. So Seiberg conjectured that versions of chromodynamics come in pairs, and that's kind of a weird combination of things. So he conjectures that if you're doing this chromodynamics with G equal to SUN, and F flavors of quarks and antiquarks, He calls this an electric theory for silly reasons. He says that this thing here, this theory, is equivalent to doing super chromodynamics with a group, which I'll put a little check on there to show you it's the dual one, SU of f minus n. So we need f bigger than n, just as a remark. And we still have f flavors of quark and anti-quark. But then he adds in some extra matter, something called what he calls mesons, but they correspond to the representation end of morphisms of C of f with a superpotential. So anyway, but I just want to point out this is kind of a crazy thing. He's saying there's a gauge theory with this gauge group, and there's another gauge theory with a totally different gauge group, and they're supposed to be equivalent. He calls this one, sorry, this is electric, and this is magnetic. Okay. So this is what people mean by Seiberg duality, is this equivalence of these two theories. If you really ask them for details, it's hard to get them. They're sort of very vague, but this is the takeaway message from all the papers.
You mean the moduli space or what?
Yeah, this is exactly what I'm saying, is that if you read the literature, they'll say these things match up, but they won't tell you like everything they think will match up or what might not match up. You know,
Classical statement or
this is a quantum statement. This is a quantum statement. So this game of going from sort of Witten's game in this holomorphic setting, people had started to play versions of this, I don't know, 20 years ago. Kevin Costello has been advocating it quite a bit and using it in lots of contexts like the ADS-CFT conjecture. But you know, anybody can get in on the game. So this guy named Richard Ager conjectured it holds that Seiberg duality holds after holomorphic twisting. Maybe it's worth remarking that for n equals 1 theories, there are no topological twists, okay? So it's just not possible. The only game in town is to try to do a holomorphic twist. When n gets bigger, you can sometimes get topological twists. So his statement, I should just make a remark. His statement, he states it as an equivalence, those who know this word, of factorization algebras. On C2, this would be some sort of analog of saying, just to give you a sense, that two vertex algebras are equivalent, like in the fermion correspondence, that kind of duality. So he's really optimistic that there's some very strong statement here about the algebras of operators being equivalent. I should also say that this is a 4D cousin of some dualities people have studied in 2D, of the Henri dualities in 2D between some Landau-Ginzburg B models. So in algebraic geometry, this is about things like homological projection duality. It's a really active area. So it's an interesting question to ask about lifting some of the things people have done in mirror symmetry type context to this 4D level.
Are the factorization algebras in one like Kara algebras, or?
Yeah, they're holomorphic in nature. So like they do, for instance, give you something that sort of behaves like a vertex operator, but in 2 dimensions. Okay, so I have, I think, 5 minutes? 10 minutes, okay, great. Oh, that's good, okay. So this is the kind of question that I think there's a lot to do here to think about the associated moduli spaces and then what it would mean to quantize them. And there's clues from boson-fermion correspondence. there's clues from 2D. I keep making these analogies to 2D about how things might go, but it's a fun game to try to figure out what would happen. Okay.
Can I ask a quick question?
Yeah.
There's a sort of stupid case of the conjecture which is n equals 1.
Yeah, sorry, I should have.
Oh, sorry, n has to be bigger.
Yeah. No, if you're doing the abelian, and there's this thing people call electromagnetic duality, which is equivalents of purportedly abelian gauge theories. That's also interesting to study. And more or less, Seiberg was just very optimistic that some pattern like that continues in a non-abelian setting. SU1's pretty boring, but you know.
Statement, but it could be true, but I don't know. I thought maybe you would say, yes, it's obviously true.
Well, there's a question. We're really careful about using SUN. It's interesting to ask, like, to extend to other semi-simple things, and then how to deal with reductive things. And then you should be combining statements like this with electric magnetic duality for the extra component. And people play this game of trying to fit it together, but this is like the most basic form of what people usually call Seiberg duality. Okay, so in the last few minutes, I've laid out this direction to go, studying holomorphic field theories, particularly stealing guesses from physicists to make guesses over here. So what can be done? And I should say, not a lot of people have explored this too much, so I'm just going to sketch what we've tried. What we've been up to.
What is the space of solutions look like for magnetic theory?
Could we talk about that afterwards? Yeah. It adds, instead of being this, it sort of involves V cross the critical locus of the superpotential, and then you're taking a quotient. So it also has a nice stacky description, or it should anyway. Okay. Oh yeah, I should have mentioned, so I did this n equals 1 case. You can ask for things for n equals 2. That would be asking for some holomorphic version of what people call Seiberg-Witten theory. Not what physicists call Seiberg-Witten theory. If you do the n equals 4 case, you could ask for a holomorphic version of what Kapustin and Witten did. Is there some version of S-duality? Okay, so the question I'd like to talk about in the last few minutes is what can be done in these directions? Nothing I've said so far is due to me. It's a sort of story that a group of people are thinking about around, sort of maybe centered around Kevin Costello and Davide Gaiotto. So there's some tentative steps. But let me tell you 2 questions to study. So one of them would be actually properly describe the classical theory, the moduli of solutions to the equations of motion. So formulate these, the variational calculus clearly enough that you can ask for an equivalence of, say, derived analytic stacks or something. So I've been giving you my guesses for what the answers are. So this is something, so the formal geometry has been done, has been explored. But the global part hasn't been developed very much. And as a subclass of this question relevant to this audience is for physics, it's important to describe these things should have shifted Poisson structures. By a mechanism akin to the AKSZ, more or less the AKSZ method. So there's a special case that people in physics tend to focus on first. You take your space-time to be c to the n, and you take the translation invariant solutions. They don't study all solutions, they just study the constant solutions. Okay, so we have all solutions for your theory on c to the n. There's a sub-locus, the translation invariant ones, and physicists sometimes call this the moduli maybe of classical vacua. Okay, so classical vacua. Okay, so for the holomorphic twists, it should be plausible that it usually looks something like this is the complexified group, some stacky quotient of a vector space by the group. That's a lovely stack, something we've studied a lot in mathematics. Let me remark, as evidence for his duality, a key piece of evidence, according to Seiberg, was that you could match up not the moduli stacks, but their affinizations, their GIT quotients. So let me use M vac, the straight M. Oh, maybe I shouldn't be using M. Sorry about that. Is the affinization of this moduli stack, which means you take spec of functions, global functions, on there. It's a GIT quotient, and so it might mean, in this case, it would mean something like the GIT quotient. Okay? And here's a cool fact. So here's the evidence Seiberg gave, was that the electric moduli space really is equivalent to the magnetic moduli space. And that's because if you take the electric space of things and you take their GIT quotient under, say, SLN, and you take the magnetic one under SLF minus n, these things are the same by a theorem of Weil. You can just find it in Hermann Weil's invariant theory book. So Hermann Weil proved this equivalence of these two GIT quotients. And then Seiberg, well, he doesn't give Weil any credit, but he uses exactly this fact. And it actually explains exactly why you need to stick in these mesons. It's just 1920s invariant theory. Okay. Let me just raise one question, and if people are interested, I'd be happy to talk over lunch about it. So one set of questions is to think about these moduli of solutions. That's classical. The second thing is to try to quantize them. And everybody has maybe their favorite way to do quantization. For me, that's BV quantization. And we've been able to, over the moduli stack of vacua, construct BV quantizations of these theories. So each point on the moduli of vacua gives you some perturbative holomorphic field theory, and you can quantize these and glue them together over this thing. This is very similar to, say, the way we do Poisson sigma model and quantize it. So we've done this for n equals 4, n equals 2. That's published, and n equals 1 we're working on. And you can get some steps towards doing a quantized version of this statement. Oh, yeah, thank you. OK, so collaborators. So n equals 4 is Chris Elliott. Thank you. Me and Brian Williams. OK, and we do n equals 2 along the way. N equals 1 is me and Brian Williams. And this is work in progress. OK, thanks for listening.